The standard reduction potentials can be found in a table. Let's examine the structure of this table. At the top, we have fluorine being reduced to the fluoride ion, and at the very bottom, we have the lithium ion being reduced to neutral lithium. Somewhere in the middle, we have the reference point for all other reduction potentials. That is the standard hydrogen electrode, which has been, by international agreement, assigned a reduction potential of 0 volts. Fluorine at the top is the best oxidizer. It is the best at stealing other species' electrons. That is, it is the best at oxidizing other things. Lithium ion at the bottom is the worst oxidizer. It is not at all good at taking other species' electrons. This same sort of story can be told on the product side of these reduction equations. If you look at the sign of the reduction potential, that sign indicates whether or not the atoms in that reduction equation want to be as they are shown on the product side or not. This positive sign indicates that fluorine badly does want to exist as the fluoride ion. On the other hand, if we look at the bottom, we see that there's a negative sign in front of this reduction potential. This suggests that lithium does really not want to exist as neutral lithium. Those are just a few general ideas to give you some sort of basis for evaluating this reduction potential table. On the left side of the table, we have metal cations, hydrogen ion, and elemental nonmetals. And you can see that in the few examples that we've shown here. We've got at the bottom the lithium ion, there's our hydrogen ion, and at the top there's an elemental nonmetal. On the product side of these reduction equations, we find neutral metals, hydrogen gas, and the anions of nonmetals. And again, you can see all of those here. We have here at the bottom neutral metal lithium. We've got hydrogen gas, and then here at the top on the right side we have the anion of fluorine, the fluoride ion. As mentioned previously, the reference point for reduction potentials is the standard hydrogen electrode, which has a reduction potential by international agreement of 0 volts. This is analogous to the arbitrary reference line when calculating gravitational potential energy in physics. We have to have some reference point that we use when referring to other values. That is the purpose of the standard hydrogen electrode. It turns out that multiples of coefficients do not affect the reduction potential. In other words, if we had 1 mole of zinc ion being reduced to 1 mole of zinc, or if we had 2 moles of zinc ion being reduced to 2 moles of neutral zinc, the value from the table, which is negative 0.76 volts, would apply to either of those cases. Or if we had some crazy number of moles, like 7.269 moles of zinc ion being reduced to zinc metal, it wouldn't matter. The reduction potential would be the same. And here's why. Because a voltage, which is the unit for potential, is a ratio of joules to coulombs. And if we have twice as many zinc ions being reduced, for example, we have twice the number of electrons transferred. The number of coulombs would be doubled. But it takes twice as much work to do that, twice as much energy, twice as many joules. So the ratio is maintained. We use the standard reduction potentials when finding the cell potential for a given cell. That is, the potential of the two connected half cells in an electrochemical setup. The simplest cell potential is the standard cell potential, which is the potential, that is the voltage, when all substances are in their standard states, namely any solution concentration being 1 molar, any reacting gas being at 1 atmosphere of pressure, and the temperature being 25 degrees Celsius or 298 Kelvin. The standard cell potential depends on the 2 half cells that are involved. One of the half reactions will be an oxidation and will thus have an equation and an E naught that will be opposite to what is shown in the table. What we're saying here at the very end, a standard cell potential depends on 2 half reactions. One of those will be a reduction. We'll use the number and the equation right from the table. The other will be an oxidation. We'll have to flip the equation around, and we'll also have to flip the sign. We'll get to that in another lesson.